Welcome back to Environmental Science, Chapter 12, and we are at our third lecture, finishing off talking about toxicology and risk analysis in regards to any kind of thing that can get into the environment and harm animals and humans, things like that. Now, for us, I wanted to just quickly show you a couple things that I've done. I've added and adjusted some slides. I'm going to upload this to the course website. And I've added in these key ideas. These help you kind of understand. These are from the beginning of the chapter in the book to help you kind of focus on what you really need to know from these sections. So this starts with key idea 1 and 2. And as we go through, eventually, also PS, I took off West Nile virus here because I forgot to put it on the last one. Going through to the end, you'll notice on the next slide here, this is where we're going to start today. This is key idea number 3. So name, identify, understand the 5 major types of toxic chemicals. And I'll point out the rest of the key ideas as we go forward. So toxicology and risk analysis. So toxicology is the study of chemical risks. And it's pretty broad, but we're going to focus down into some of these ideas here. First, let's identify these 5 major toxic chemicals. I'm going to go ahead and get my laser pointer out of here. There we go. One classification are neurotoxins, so that disrupt our nervous system. These could be insecticides that get into the water system. Lead is a neurotoxin. We've talked about lead in the past. And also mercury. We've seen that accumulate into fish sources, tuna, things like that. So those are our neurotoxins, think nervous system. Carcinogens are cancer-causing or potentially cancer-causing compounds. So they inflict damage to our cells. Tobacco use is one of these. The radioactive element radon you can find in soil and water. And asbestos, the insulation material naturally forming or naturally found that was used for years and years and years. Teratogens are chemicals that can mess up our embryos and fetuses, so the birth cycle. Alcohol is the most common one that we might think of around today. That's why we tell pregnant women to definitely not ingest any alcohol. And then in the, I forget, 1970s, 1980s, some medications like thalidomide, this morning sickness drug, was used and prescribed, but it turned out for pregnant women, it turned out it actually really had a bad effect on embryos and fetuses. So those are the first 3. And here is a figure from the book just showing some statistics on lead. Lead is a really big problem, especially for the development of young children. So the safe level is in milligrams per deciliter, milligrams per of blood concentration, and 0.1 is considered safe. 1976 to 1980s, we saw really high levels. So we started to phase out lead in things like paint and gasoline. And through the years, that level, blood concentration of lead in children has gone way, way, way down. Last 2, allergens. We should be familiar with certain types of allergens. So these really help cause allergic reactions in our system. Nuts, certain types of antibiotics, animal danders. A lot of people are allergic to dogs and cats, things like that. And then the last ones are endocrine disruptors. These are chemicals that actually mess with our hormonal system. So sometimes we have medications that regulate our hormones that people get rid of in improper ways that get into our water systems. Pesticides can have different structures that actually mimic hormones. So, or basically go into the areas that hormones would go into in our bodies and disrupt our hormonal cycle. And this picture is from the book, and it kind of shows what could happen with a healthy system here. So hormones are these molecules that travel through our blood, and they trigger certain things in our body. And within this endocrine system, that can be the growth of our bodies, repair, sexual function, reproduction, really important things. And they're really powerful. You don't need a very high concentration of these hormones to produce these really important effects in our body. So if you disrupt that system with something like an endocrine disruptor, so this might go into this receptor instead, it's going to block the normal hormonal function. So these small changes in our concentrations of hormones or the addition of endocrine disruptors can have really significant effects on our body. So those were the first, well, those were the 5 types of toxic chemicals we're going to be talking about. And that was key idea number 3 here. Key idea number 4 here. So this says scientists can determine the concentration of chemicals that harm organisms. So we're going to talk about how we identify the concentrations that harm us, the studies that go into it. So key idea number 4 says distinguish between dose-responsive studies versus retrospective studies and prospective studies. So what are dose-response studies? Well, basically a scientist would give specific doses of a chemical to animals like mice, rats, pigeons, and trout, not humans. We don't do human trials, but for mammals, mice, and rats. Bird species, you would use trout and pigeon? No, pigeons. And for amphibian species, trout are used. There's other species as well, but these are the type of animals. So we would give them a specific concentration and see what happens. We use this term called LD50, lethal dose. That is the amount of the chemical that kills the individuals, or kills 50% of the individuals. And we use this value to kind of determine what items are more toxic than others. And you can have really high variation of what the LD50 is. I'm actually going to jump to this graph. I'll come back. This is what we mean by LD50. So if you have 0, you've got 0% mortality. So 0% of the population that you're studying, like 10, 20, or 100 of these mice, for example, would die. Then once we get up to, let's say, 4 units, now maybe 10% of your population would die if you gave them that much. LD50 is the concentration of the chemical that kills 50% of your population. So 50% survived, but 50% died. So that's the kind of number that we use to compare other drugs to each other. It doesn't mean like the rest of the 50% that survived are healthy. It's just that they didn't die. So I looked up some values on Wikipedia because I was curious, and these all use rats as their study. That's also important too, to understand what animal they're using. And we would use rats and mice to extrapolate what their effects would be on humans. So sucrose, so the table sugar essentially, would be 29,700 milligrams or 29.7 grams per kilogram of mass of that rat. So if the rat weighed 2 kilograms, you would multiply that LD value by 2, and giving them that much with that weight, that would be their LD. Actually, I should have put here, these are LD 50s right here. Ibuprofen for rats, 636 milligrams of ibuprofen for a kilogram of body mass. I looked up some conversions on this on the internet, and it seems if you scale this up to humans and extrapolate out, LD 100 means pretty much 100% of the time, 100% of your population would die if you ingested an entire large bottle, like a 500 pill bottle of ibuprofen. So it's pretty tough to get 100% overdose rate on something like ibuprofen, but you could do it. It would just take a lot of it. And again, that's 100%. If you took an LD50 amount, you might die as well, just a lower chance. For rats, I looked up nicotine. So notice ibuprofen down to nicotine, only 50 milligrams per kilogram of body mass for a rat. And then batrachotoxin, I'm not exactly sure how you say that, but this is the poison, it's from a toxin from poison dart frogs. And I converted it, it said nanograms on the internet, I converted that to milligrams, 0.000005 milligrams per kilogram. That's all it takes for a LD50 value for a rat, or 5 nanograms. So you can see the really high variation in LD50 values for some of these compounds. They also do just harmful effect studies. So instead of seeing how many of the population dies, you could see this effective dose, ED50, that causes 50% of the animals to display some sort of specific but harmful non-lethal effect that you're looking at. Maybe there's a respiratory issue, or maybe it physically slows the animal down or something like that. You would look for that effect as your ED 50 value. So 50% of your rats are slowing down, for example, not dying, but they're looking at specific harmful effects. However, the LD50 values are usually what are spoken of in day-to-day talk for chemicals. I also was curious, in the book it talks about this, I added this into the slide. What is considered a safe level of consumption? For animals, you would divide that LD50 concentration by 10 and say that's somewhat safe for animals, or relatively safe. For humans, a different standard, much higher standard is used. You would take, let's say, an LD50 value for rats or mice or something. Let's say it's 100 milligrams per kilogram of body mass, and you would divide that by 1,000. And that's what we would say is a safe level of consumption. So quite a bit less than the typical LD50 value is what we say is a safe level of consumption for humans. And that was that graph that I showed you before. So within this, looking at dose response studies, most of the time these are short studies. You're giving them enough chemicals that affect them very quickly. So short term, last only a few days. These acute, and we call those acute studies. There are chronic studies though, so that's trying to find long-term exposure at low dosages. So maybe someone's getting exposed to something in their workplace little by little over a long time period. These are much more difficult to do, but they offer really good information. Most of the time, people in a workplace are being very safe, so they're not being exposed to large acute amounts unless they somehow ingest it, or some, if you spill in your body, they can go through your system really quickly. Most it's just a chronic exposure, long term. So chronic studies are also really important to do along the acute studies. These photos are from your textbook showing some experimentation of dose response experiments. This one on the right showing the use of tadpoles for amphibious versions of animals, doing some different insecticide experiments. So probably dissolving some insecticides in their environment, in their water, specific concentrations over a few days, or maybe it's a long-term test. And this over here, honestly, on the left, I'm not exactly sure what's going on here. They just said that this is a study. So those are the specifics of dose response studies. Now we're going to take a look at epidemiological studies. So well, this is a tough one. Epidemiology, that is always a tough one for me to say. Epidemiology is the study of the patterns of diseases. So what are the causes? What are the patterns? Where do they come from? It's the whole study of diseases. And we're going to talk about retrospective, what happened in the past, and prospective, what can happen in the future. So retrospective studies, these are people or animals that have already been exposed. So sometime in the past, maybe it just happened, maybe it was a week ago, a year ago, but they know for a fact that they've been exposed to something. So you're studying a population after the exposure to try to find correlations and conclusions. Prospective studies, though, monitor populations that you think might become exposed. So you would ask a large population of people to check in with you over a certain period of time and ask them, what things have they exposed themselves to? Maybe it's a specific type of food you're studying. Maybe it's simple as tobacco or alcohol use. And so in the future, you expect them to be exposed to it, and you ask them the health effects after that exposure. This is an example from the book of showing a retrospective study. So there's a huge chemical disaster in 1984, methyl isocyanate gas, and it was released and injured many, many people. So they did retrospective studies on stillbirths and also respiratory symptoms, and noticed the ones that were exposed, there's an 80% frequency of respiratory symptoms versus not exposed, a little less than 40%. So there was a pretty strong correlation with respiratory symptoms after the exposure to this isocyanate gas. This is also very important. Understanding the fact that two different risks come together can give you a harm that wouldn't come about with just one or the other. So the example they give here is asbestos. You inhale asbestos and it causes many respiratory problems. Versus separately, tobacco can also cause cancer and respiratory problems. But together, smokers who ingest asbestos have an even worse, something even worse happens. So there's a much higher effect for smokers for asbestos. So that would be a synergistic interaction there. All right, moving on to key idea number 5. So now we're actually going to where do these chemical sources come from, basically? So trying to identify the factors that help determine the concentrations and how we actually experience these concentrations of chemicals. So first thinking about where do they come from? What are the different routes of exposure? For humans, there's actually not that many, really. I mean, that's at least that's nice. We can identify most of the time where they're coming from, or at least the routes of where they could come from. So we ingest food and liquids, things like that. We breathe the air, that could be a route of exposure. Water systems, so simply our drinking water, or exposed to water systems, lakes and rivers, things like that. And through the soil, that's another one, big one, plants and soil. And then fetuses and babies have the exposure directly through their mothers or their home environment, things like that. When we talk about chemicals and where they come from, a lot of times we're thinking, are they more water soluble? And if they are water soluble, they get washed through the soil a lot easier, so they don't accumulate in the soil very long. If they're not very soluble in water, rain and runoff does not take them out of the soil very quickly, so they can be found on the land a lot longer. So we think of solubility and how they can bioaccumulate with this idea. So solubility is how well a chemical can dissolve in a liquid. And most of the time we're thinking about how well they dissolve in water. But some of them actually do dissolve in oils and fats. So depending on their structure, you can dissolve chemicals very easily in a fatty oil versus water. And that kind of determines where they end up out there in the world. Oil soluble chemicals, these fat soluble ones, these, when they're ingested into our body, can be stored, or animals especially, because that's where you would get them from. If an animal ingests a pesticide or something that's fat soluble, it'll stay in their tissues. And as they continually get exposed to that same chemical, that's called bioaccumulation. Then more and more and more of it is stored in their fatty tissues. So bioaccumulation is an increased concentration of that chemical within an organism over time. An example of this is, let's say, well, this is very related to biomagnification. We talked about this in the water chapter. We kind of went through this with, I think, lead and tuna, things like that. But let's take another example here. DDT is a common, well, it used to be a lot more commonly used as a pesticide, and also you can still find it used in things like mosquitoes, bug repellents. But there's a lot of regulation on this. The LD50 of this in a rat is 113 milligrams per kilogram. So scaling that up to a human, it's moderately toxic. But let's say DDT gets into water. This happens to be somewhat water soluble, but it's also fat soluble. It can kind of be in both. So if it gets into plankton and it's at 0.04 parts per million, and then as the stickleback fish eats that, it accumulates to 0.26. And then as summer flounders eat a bunch of these, it gets even more to 1.28. And finally, an osprey eats a bunch of flounders. We finally get up to an osprey, and it's at 13.8 parts per million inside the osprey. Not only is that bad for the osprey, it could be bad for any other animal that might eat that osprey. This happens with tuna. Lead gets into the water through pollution from coal, mostly. Then fish eat the contaminated plankton, contaminated fish, and the big tuna have have a lot of lead, and then we can ingest that. But the importance comes to where do those chemicals end up. If they're very water soluble, they're going to get into the water system very easily. But DDT, on the other hand, really sticks into the soil for a long time. Eventually, it does get run off into oceans and things like that. So speaking of that, persistence is the term we use. So how long do those chemicals stay around? We use the term half-life. So how long does it take for half of its concentration to disappear? And looking at some of these chemicals, Roundup, that Roundup brand herbicide, between 7 to 70 days in water, it takes for half of it to disappear. So 7 to 70 days, if it's 100 parts per million, it's still at 50 in 7 to 70 days. Look at DDT in soil. That's really interesting because it can stay just in the soil. So if it's a pesticide and we're using it on our plants and we expect that it just washes away, it does not. It stays inside the soil for 30 years. So if you have 100 parts per million in the soil, 30 years from now, you're going to have 50 unless you do something else to try to clean it up. So left alone. That's why DDT has been highly banned throughout the world for many, many uses. It's still used in some things, but not very often you'll see DDT being used anymore. It's certainly not as a good pesticide or herbicide. So how do we keep track of this stuff? And actually, we have to identify these risks. We're not just going to ignore them. So we go through this process, assessing them, finding out where what the actual chemical risk is, determining, an accepted value. It's like, okay, we accept it as this much. We're going to accept that, and then how do we manage it? How do we regulate it? What laws and rules we put in place? So that's this section of the chapter. Well, qualitative is the kind of risk assessment that a lot of us use every day when we're just thinking, what is the risk that I'm going to get in a car accident today versus get hit by a bus or something? We're just kind of using the perceived risk to make decisions. So they're not really based on data a lot of the times. And we're trying to think, what's the most likely event that would happen to us? What's the probability? The book uses this. Oh, this is basically the same thing. Perception that certain behaviors or activities entail high risk does not always reflect reality, the actual risk. So this is a good example, and this really hits home to me because I think about this a lot. I am not a good flyer. I really don't like airplane rides. They freak me out, and for not any actual reason, right? It's a perceived risk. I get an airplane, and my perceived risk is this is really scary, and I have a high chance of dying. In reality, it's much more dangerous to ride in a car, an automobile. But I can sleep like a baby in a car on a cross-country road trip, and you cannot find me sleeping for more than 20 minutes in an airplane because every little bump wakes me up. So perceived versus actual. The actual risk to life is much, 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 much lower for flying than it is driving a car. So when we're making risk management policies, we don't really want to use perceived. We want to use actual risk analysis. So we need to do some assessment, identify the hazard, characterize it, determine acceptable level of risk, and then actually make some policy. And to determine the actual risk, we use the probability of exposure. This is the quantitative based on data. Probability of exposure times the probability of being harmed if you're exposed. So probability of exposure is just how often do you think you're going to come in contact with that. And then this is really the toxicity. What's the probability of me being harmed if exposed to it? What's the LD50 value, for example? Here are some of those probabilities turns into thinking about deaths in the United States. So for me, let's find the old airplane accident. 1 in 5,051. I don't know why I'm so afraid of airplanes given how low the risk is versus motor vehicle, 1 in 84. Think how high that is versus airplane. I should not be worried about that, but it's a psychological perceived risk. So when doing risk assessment, we want to be really careful about those. If you look at heart disease and cancer in the United States, 1 in 5 and 1 in 7 probability of dying. But a lot of people do not take this into account thinking of their daily lives. Think of how much of us, for example, look both ways when we cross the street, wear life vests, put on sunscreen and drink water, make sure we don't go outside during lightning storms, right? We definitely are careful about that, aren't we? But a lot of us don't think about these. So we need to shift our focus from perceived risk to actual risk to help manage and plan on some of these risks. This is a case study from the book. This shows the process of assessing a risk, determining proper levels, and then managing it, forming policy. So in the Hudson River, New York City, and Silver Lake in Massachusetts, they found lots and lots and lots of PCBs, these chemicals that were being dumped from electronics companies that they were used in the manufacturing process. They're being dumped illegally. So the risk assessment, they found out what was in here. They determined a level of toxicity that was acceptable. And they determined a level of toxicity in these lakes was not accessible for people to be swimming or fishing in. So that was the management. The management means this. They had to close off access to these lakes and rivers because of the accepted levels they determined were too high versus what they would be what would you want to interact with to stay healthy? Okay, finally, we're getting down to the end here. If you're thinking about assessment and management, there's a couple of different philosophies we're going to talk about here. One is innocent until proven guilty. This means that, let's say you have a new sunscreen and you get it to the market, and basically you would say it poses an unacceptable risk only if proven so in practice or by research. So that's just saying, hey, listen, I'm going to get this thing out here, and until you can prove to me it's harmful, it'll stay on the market. The other side is if a hazard is even plausible but not proven, on the front end, you're going to take a lot of steps to reduce or remove the hazard. This is more business friendly, getting stuff to market quicker, getting your products out there. This is more red tape, but a lot more conservative approach and safe approach to releasing products into the market, things like that. So this is their example. Let's say this is your sunblock or something. This is the innocent until proven guilty method. Basically, you research it, no pre-market testing. You do some post-market testing after it gets out there. Finally, you realize it's not safe after these three steps. Like, oh, and then you finally have to do some regulations to make this safe consumer product. However, precautionary would say do your research, you do extensive pre-market testing, and only the safest products out of those are brought to market. And then you've got this safe product available to consumers at that point. So it takes a lot longer to get that to the consumer. And then you also have required post-market testing, even after it's determined fairly safe. So a lot of more front-end safety and precaution with the precautionary principle than the innocent until proven guilty principle. So there are some international kind of agreements on what chemicals should and shouldn't be used. So this happened in 2001. 127 countries met in Stockholm. So it's called the Stockholm Convention and Stockholm Agreement. And there was 12 chemicals, these quote dirty dozen. These included DDT and PCBs, and other chemicals that a lot of them are byproducts of manufacturing. So chemicals that companies have to safely dispose of when they're done in the manufacturing process. So we have this Stockholm Convention and Stockholm Agreement that determine that. This photo is showing the fact that now we know asbestos is bad. Back when this was used, we used as insulation, and it sounds like we really took this innocent until proven guilty principle. As in, we found out it worked really good for an insulation, so we threw it into millions of homes, realized later it was bad, and now we actually have to have regulations. And we really should have done extensive testing first to make sure that it was a safe consumer product. So now we have people having to remove it from homes physically after the fact, rather than identifying it unusable and unsafe before we had this really big problem. I just wanted to highlight the key ideas of the chapter here. This is the end of the chapter. This is from your book. Go back and pause this slide. Read all this stuff to give you an idea of what we went over. And this is in your book, so remember that. And then as always, here are the review questions that you can go through to help review the material from the book. All right. Thanks for listening, class, and I will see you next week to start the next chapter.